Welcome to Epsilon Pro Academy. This lesson is literally designed for examination purpose, and we will be dealing with calculation under magnetism. So in today's lesson, we are going to be looking at magnetic field near a long straight wire under Biot-Savart's law. So let's consider the first question on the board. The question is, consider three long straight parallel wires shown below. Find the force experienced by a 25 centimeters length as wire B, and the diagram is given on the board. Now, before you can be able to attempt this question on the board, let us examine the diagram or emphasize on the diagram. On this diagram, there are three wires, three parallel wires, A, B, and C. However, the question said, find the force experienced by a 25 centimeters length as wire B. That is to say, wire B is our area of focus or interest because it is isolated. Wire B is isolated, meaning that wire A will produce a magnetic field at B, and wire C will also produce a magnetic field at wire B. Then these two magnetic fields would combine to produce a net magnetic field on wire B. So just take note of the concept. So let us record that the force experienced F, the force F is equal to B I times L, where F is the force experience, B is the magnetic flux density or magnetic field. So B is equal to the magnetic flux or the magnetic field, and it is measured in Tesla. I is the current, while L is the length of the wire in the magnetic field. At this point, we cannot calculate the force experienced without knowing the magnetic field produced by wire A and wire C at B. So the first thing we have to determine is the magnetic field produced by wire A at B and wire C at B. So to do this, let's record this formula. Let's record that magnetic flux density is equal to magnetic field B is equal to mu naught. Mu naught is permeability of free space, and it is measured in Henry per meter. While I is current measured in ampere, and X is the distance given, which is also measured in meter. So this is the formula which will be used to determine the magnetic field produced by A at B, and also the magnetic field produced by C at B. So the first step is that we are going to determine the magnetic field B produced by A. So magnetic field B produced by A at B is B, comma A. Magnetic field produced by A at B is given as this, and the formula will be equal to mu naught times current at A divided by 2 pi X. Then the distance B A, the distance AB. the distance AB. All right, now magnetic field BA is equal to, now note that this is a constant, and this constant is 4 pi exponential negative 7 Henry per meter. Take note of the constant, which is permeability of free space. So permeability of free space is given as 4 pi times 10 raised to the power of minus 7 Henry per meter times current. Current at A, flowing at A is 30 ampere. 30 ampere divided by 2 pi times the distance between AB is 3 centimeters. Always ensure you convert from centimeters to meters. So conversion standard, 3 cm will equal to 0.03 meters. Divide this by 100. That is all. So we have 0.03 meters. I will substitute 0.03 meters. So magnetic field is equal to, now this is where most students make mistakes. At the numerator, most of you obtain error after typing 4 pi exponential negative 7. This is how we obtain the right result. 4 times, put the symbol for times. 4 times, then press shift exponential in your calculator, you obtain pi, symbol for pi. 4 times pi times another symbol for times, then add exponential negative 7 to it. Then multiply that by 30, we obtain the result for the numerator. 3.7699 times 10 raised to the power of minus 5 divided by 0.188496, and this will equal to 2 times 10 raised to the power of minus 4 Tesla. Magnetic field is measured in Tesla, so we have successfully obtained the first step, and the first step was to determine the magnetic field produced by A at B. Now the next step, which is step number 2, we are going to determine the magnetic field produced by C at B. That will give the magnetic field produced by C at at B is B, C, which equal to mu naught times current at C divided by 2 pi, the distance between B, C. The distance between B and C. So we obtain BC is equal to, now the constant for mu naught is 4 pi times 10 raised to the power of negative 7 times, multiply this by the current at C. The current at C is 20 ampere. So we obtain 20 ampere divided by 2 pi times the distance between B and C on the diagram is 5 centimeters. So converting 5 centimeters 5 cm is the same thing as 0.05 meter divided by 100. So we have times 0.05. Magnetic field produced by C at B is equal to 2.513 times 10 raised to the power of minus 5, or divided by 0.3142. Point in Tesla. So the magnetic field produced by A at B, 2 times 10 exponential negative 4 Tesla, whereas the magnetic field produced by C at B is 0.8 exponential negative 4 Tesla. Now we have successfully obtained step number 2. Let's look at step number 3. Step number 3 is to determine the net or total magnetic field. Produced by A and B at, produced by A and C at B. So total magnetic field B net. Now B net to get B net or the total magnetic field produced by A and C at B, we have to take note of this rule. The rule is that subtract when moving in opposite direction. That is the first rule, A. And the second rule is that add when moving in the same direction. Now we subtract, also add if they are moving in the same direction. Now how do we know when they are moving in the same direction or opposite direction? Now let us say that all the current pointing upward should move in a clockwise direction, whereas all the current pointing down should move in anti-clockwise direction. The current pointing upwards should move in a clockwise direction, whereas the current pointing downward should move in anti-clockwise direction. So let's say upward current should move in a clockwise direction, and the downward current should move in anti-clockwise direction. Haven't known this, Let's move the magnetic field around the ring in this loop given to us on the diagram. Let's consider a new diagram. So we have 1, 2, 3. This is A, B, and C. This is upward direction, downward direction, and upward direction. Now, the concept is that when moving up, upward current should be in a clockwise direction, whereas downward current should be in anti-clockwise direction. Current B is the reference point. That is to say, current A will produce a magnetic field at B, and current C will also produce a magnetic field at B. If I move the magnetic field around the ring, this is how it will look like. Okay, and we also have this. If I move from C around the ring, it will look this way. Okay, now this is the diagram. We said let upward current move in a clockwise direction. This person produces to B, and this person also produces to B. This is their point of intersection. They are meeting at this point. Now, because they are meeting at this point, let us know the direction of the current. From C, it is pointing upward, indicating that it will move in a clockwise direction. It will move in this direction and not in this direction. So moving in this direction, to the point where they are meeting, the direction becomes this way. Now, this is the direction of the magnetic field from C to B. Let us also note the direction of the magnetic field from A to B. Then, if I'm moving from A, because it is pointing up, we said upward current should move in a clockwise direction. So it is not going this way, rather it will move in a clockwise, which is this direction. If I move from here down to this position, where these two people meet, then it will show that it is moving in this direction, this direction. At this juncture, we can say that wire A and wire C are meeting at opposite direction, because C is going this way and A is coming this way. So they are moving in opposite direction, Then when moving in the same direction, the diagram will look this way and this way, or like this and this. But when moving in opposite direction, it is always pointing at each other. So to determine B net, which is the total magnetic field, we are going to add this. We are subtracting this from this, because they are moving in opposite direction. So when moving in opposite direction, the rule states that we should subtract. But when moving in the same direction, the rule states that we should add up. That is the simple concept. So B net becomes B of C minus B of A. B net is equal to the magnetic field produced by B at C minus B A. So we are subtracting because they are moving in opposite direction. So that becomes B net will equal to magnetic field produced by C at B is 0.8 exponential negative 4. 0.8 times 10 raised to the power of minus 4 minus magnetic field produced by A at B, which is 2 times 10 raised to the power of negative 4. B net is equal to so we obtain B net or B total as minus 1.4 exponential negative 4 Tesla. From the question on the board, find the force experienced by a 25 centimeters length as wire B. So the force F is given as B I L sine theta, and B net is equal to minus 1.2 times 10 raised to the power of minus 4 Tesla, I, which is current. The current at B is given as 10 ampere. 10 ampere. Up next is the length of the wire in the magnetic field, and the length of the wire is given as 25 centimeters. So 25 cm convert to meter by dividing this by 100, and it will yield 0.25 meters. Then theta is equal to 90 degrees, and sine 90 degrees would give 1. Now take note of this. In every long straight wire, the magnetic field is always tangent to circles around the wire. The magnetic field is perpendicular to the direction of the current in that wire. Since magnetic field is perpendicular to the wire B, so theta equal to 0, and sine theta or sine 90 degrees is equal to 1. So at this juncture, we can substitute this into our formula, where F is equal to B times I times L sine theta, and B or B net times current at B times the length of the wire in the magnetic field B, then sine 90 degrees. So F is equal to B net is given as minus 1.2 times 10 raised to the power of minus 4 Tesla times I is given as 10 amperes times, and the length is 0.25 centimeters. So F is equal to 3 times 10 raised to the power of negative 4 in Newton. This is negative, so the negative sign has no bearing or effect on the force. It is showing you the opposite direction of the force in the magnetic field, and this becomes the final result. So from the question, we were required to determine or find the force experienced by a 25 centimeters length as wire B, and the force experienced is equal to 3 times 10 raised power of minus 4 Newton. Let's consider another question where the direction of the current in this loop will, okay, let's say the first direction will point up, B will also point up, and C will face down. Then we will be required to determine the length of B in the question. So let's look at example number 2.